Solubility of the grams of the salt in 100 grams of water. That's one way to measure solubility. And what's most notably about here is when you have, for most of them, because they slope upward, the slope is a positive slope. There's only a few where it has a going down or decreasing slope. You're going to find that as you increase the heat or give it temperature, heat plus your solid, is going to give you your ions here. So most of these dissolving processes are going to be endothermic, because if you add heat to it, you should be able to dissolve more. So most are going to be endothermic. There are a few exothermic ones on here. The Ce sulfate here, that's one example. They're not as frequent of exothermic, but there are some. In most cases, most of your common salts that you see on the curve here, like potassium nitrate, has quite a slope. The sodium nitrate's definitely way up there in terms of temperature. You can dissolve a lot. One you should most notably note as well is table salt. It's almost a flat line, so temperature doesn't really affect its dissolving ability all that much. It's kind of different too. In that case, it's almost completely flat, so it really has its saturation point there. Okay, so heat plus the solid, most of these are endothermic. Okay. Molar solubility is a specific amount too. It's going to be the number of moles per liter of solution, which is just molarity again. So we're going to be measuring our molar solubility in terms of molarity, moles over liter. Okay. So keep that in mind. Another way to measure solubility. And we'll be, when we're talking about Ksp and talking about equilibrium, we're really referring to molar solubility. We won't be looking at the grams per 100 grams of water. We'll be looking at the moles per liter of solution here. Now for some examples of how to think about molar solubility. Take a look here. This is kind of a review of Unit 1. See what you can see here. So looking here at aluminum sulfate. We're saying the molar solubility is 0.5 molar. What would be the saturated concentration of aluminum? And what would be the saturated concentration of the sulfate? So once again, we're realizing this is back to Unit 1 stuff. We're talking about the Al2 SO4 3 is your solid here, and it's going to form 2 ions of the aluminum and 3 ions of the sulfate. Okay, so you have your stoichiometric relationship. You can do this by stoichiometry, or you can do it the faster way of like just looking and thinking of the ratio based off of the subscripts, which also basically is the same thing as the molar relationship in the reaction here. 2 of the aluminums for every 3 of the sulfates. Now remember, this is only one formula unit, right? One formula unit. This is 0.5. Okay, so if that breaks apart, okay, then you should get, for every one that breaks apart, you should get 2 aluminums out of it. So if you have 0.5 of the crystal, you should end up getting how much of the aluminum? 2 times it, so this would be 1 molar, good. And then this one would be, every time you would get how much of your sulfate out. Every time that aluminum sulfate broke apart, you would get 1.5. Now, for those that are having trouble, visualizing this, like I said, you could do it the stoichiometry way. You could do 0.5 molar of your aluminum sulfate, or you can make this moles over 1 liter, and if you really wanted to, so 1 mole of your aluminum sulfate is going to be how many moles of aluminum? it would be 2 moles, right? So if you really wanted to set it up with a track, you could do it that way. This would cancel, but you still end up with moles over liters, so you still end up with a concentration. Okay? So if you need to visualize it this way, that's fine. Okay, you're welcome to do it that way. This is faster though. And remember, on AP exam, you want, to speed up your skills because time is of the essence on that AP exam. So you could approach it this way if you really wanted to. Okay, any questions about that before we move on? This is kind of review of Unit 1 stuff though. Remembering that one formula unit breaks apart, you're going to get 2 to 3 of those different ions. All right, so now, looking at it, okay, so there's the answers. Yes, so it'd be 3 times molar solubility. The molar solubility is the 0.5. The aluminum concentration would be double. The sulfate would be triple. Now, for the second part of the example here, you're being given the aluminum's concentration and being asked to figure out the molar solubility of the compound and the sulfate. So yes, they're going to be the same answers, but let's work it backwards so we can see it from that standpoint. Okay? So once again, if you wrote out your equation here, right, your equation. So right here now, this is the 1 molar. Should be able to go backwards and forwards in any part of the equation. So for every 2 of these, how many of this do we have? 1, right? And we have 3 of those. Okay? So once again, you could set it up using a stoichiometry chart. You could do 1.0 moles of my aluminum per 1 liter. Now, moles of aluminum going to moles of, the first question was going to sulfate, right? Moles of the sulfate. So, using our stoichiometry here, what's that going to be? This is going to be a 2 down here. This is going to be a, so where does that 3/2 come from? It's basically based off of the molar relationship. So feel free, if it's better to visualize it that way until you pick up the skills faster. And this ends up being, of course, 1.5 again, right? Same answer. You could set up and work it backwards the other way too, where you had the 1 mole of your aluminum per liter, and then we have our 2 moles of our aluminum, and we have our 1 mole of the aluminum sulfate solid, right? Here's our 1 mole to our 2 moles. So basically 1 divided by 2 is going to give us that 0.50 that we were looking for the formula unit. Okay? So feel free to work it that way if it's easier. If you can't visualize by the subscripts are faster, definitely. It's a faster way to process it, and hopefully you'll accumulate those skills and be able to go faster because, like I said, time is an issue on the AP exam and on tests and so forth. So, okay? Now, there's our answers. Yay, good. Okay. What is Ksp? Ksp is known as the solubility product. It's the equilibrium position for dissolving ionic solids. When you dissolve an ionic solid, it's going to just keep dissolving until you get to that saturation point where nothing else will dissolve in the solvent. Most of the time the solvent is going to be water, so we'll be talking about it in terms of dissolving in water. Okay? So the K is just that equilibrium position. You get to that saturation point, you can't dissolve anymore, and you try to add more solid, it just dissolves at the bottom and forms a supersaturated solution. Now, of course, you could heat it up, and most of them, if you heat it up, you can add more to it. And cool it down, and then it's a supersaturated solution. However, we're looking for that equilibrium position as to how much is going to be able to dissolve into the water. And remember, the Ksp values are really focusing on the side of the solubility chart for the ones that are considered insoluble, not the ones that are soluble. We're looking at the ones that are insoluble. The Ksp values become more of a reference point to seeing how soluble is that insoluble solid. Okay, it's a gradient. It's definitely a difference based off of the Ksp as to how much is going to dissolve. So how would you write out the Ksp expression? You would just do it like we did before, only including the AQs. The solid does not count, right? You don't put that in the expression, so there's never going to be anything in the denominator. So Ksp is always just going to be the ions times each other raised to the power of their coefficients, just like we did before, the law of mass action. The only thing is you're just going to be missing the bottom portion because your thing that's on the reactant side is always going to be a solid. So it's never going to be included into the equilibrium expression here, the Ksp expression. So we won't ever need to include the solid. You'll never have a denominator in your expression when you're writing out Ksp. So let's look at the example here for the next one. We're not going to include it. Remember, solids and liquids, we don't include them because their concentrations don't change. So here is an example of the bismuth sulfide dissolving. Sulfides are on the insoluble side of the chart, so at a given temperature, we would write out our Ksp expression only including the ions. And the bismuth has a coefficient of 2, so you're going to raise it to the second power. And the sulfide over here has a coefficient of 3, so you'd raise it to the third power to get your Ksp expression. So it's the same thing, except for this doesn't count because it's a solid, so you would not put it into the expression. Nothing is going to end up on the bottom. Okay, so far? Pretty much kind of review little nuances with equilibrium here. And do remember, if we change the temperature, the K value will change here too. Most of them are endothermic, so if you raise the temperature, most of they'll be able to dissolve more. So what does that Ksp value tell us? Gives us information about how soluble that compound is. How soluble. A large Ksp value, which are going to be the ones that are on the soluble side of the solubility rules, like sodium chloride, your alkali metals, your ammonia, your nitrates. Those ones are the soluble ones. So the large Ksp values are what they're going to have. And we consider the compound to be soluble. That's how we would say that. And here's actually the designation. It has to, when you dump it into the water, it has to be able to dissolve enough to make a 0.1 molar solution. It has to be able to make at least a 0.1. I mean, it could make a 0.2, 0.5, 1.0, but it has to be able to at least dissolve enough to make a 0.1 molar solution, to be considered on the soluble side of the solubility rules. So I could keep pouring in the salt crystals into the water, and it has to dissolve enough to make a 0.1 molar solution. So that is what the definition term value we're going for to be considered soluble. So that's why 10 to the minus 1, right? 0.1 is 10 to the minus 1. Correct? My math right today? Sometimes it's not. Because that 10 to the minus whatever is going to become a good reference point in evaluating your Ksp values. So on the other side of things, a small Ksp value, the small one is going to tell you we're not soluble. Not very soluble here. And that has a degree here. So anybody on the insoluble side of the solubility rules, your carbonates, your phosphates, the sulfides, like the silver chloride, remember the silver lead examples that are exceptions. It's following the 0.001 molar. It can't dissolve and reach that 0.001 molar amount. So we would consider anything that can't dissolve and get up to, is less than that 0.001 molar is considered insoluble. Now that means this is 10 to the minus 3, right? So that means there's a range from the -1 to the -3, right? And guess what? The ones that fit in that range are called slightly soluble salts. So you have insoluble, slightly soluble, and soluble. 3 definitions here. Given that fall in between those extremes are those slightly soluble salts. So let's make sure that we're keeping a conceptual idea of when you look at that Ksp value, you should be able to go, oh yeah, that one's not soluble at all, or that one's more soluble than this one. Referencing that Ksp value be very helpful to you. Okay, so let's look at some Ksp values and take a look at the different ranges of them. So if we're looking here at this chart, and you have a chart in the back of your book that you're going to need for the problem set. It's on page 1063. This is your table that's going to have your Ksp values. So you might want to write that down. You're going to have to look those up for the problem set. But here's one I found that has a good range of different ones. So we range from something that would be in like more of the slightly soluble range here, which kind of makes sense because it does have lithium, and they basically say that all the alkali metals make things soluble. However, and that one's kind of in the slightly soluble range, I would call that. Looking at the aluminum hydroxide, we're into the 10 to the minus 33 there. That one's very, very insoluble in comparison to something that's like 10 to the minus 5. That one's still insoluble, but this one dissolves a whole lot less. The aluminum hydroxide dissolves a whole lot less than the lead chloride over here, lead 2 chloride, okay? So keep that in mind in looking at these numbers. 10 to the minus 29, very, very insoluble. The gradient, it's a range. And, we're going to be looking at, they like to use the silver chloride. We have that in kind of our examples here. 10 to the minus 10, that's pretty low number, okay? So evaluate your KSPs, looking at in terms of what they mean. Difference between solubility and KSP. The KSP gives a general idea of how soluble the compound is. And to know exactly how much solid will dissolve, we need to calculate the molar solubility. Using our KSP expression, we would plug in the concentrations and we would calculate to figure out that molar solubility. Okay? From our KSP value, we can calculate it, or they can give us the concentrations and we can calculate KSP. So we're going to calculate and take a look at how to do that. And these ones follow patterns, so they're nice and easy to follow. Just reviewing one more time, molar solubility is really just the molarity, the moles per liter, and we're going to be using molarity as our units when we start calculating here. The first pattern that you're going to see is the 1-to-1 ratio of the ionic solid. So I'm going to do a generic, and then I will show you an example that would fit that 1-to-1 ratio. So AB is our solid. And it's going to break apart into A plus AQ and B minus AQ. So an example of one like this would be silver chloride. It's a 1-to-1, right? 1 cation, 1 anion. Now if I were to write out the KSP expression here, it's going to be the concentration of the A times the concentration of the B, like so. They're both coefficients of 1 in the equation, so we don't have to raise it to any powers here. But now if you think about it, this is like our X value. And every time that one breaks apart, how many of these are you going to get? 1. So that's also like X. You're just going to get 1 of it. We have 1 of these, that's going to make 1 of those, and this is going to make 1 of those. So this is like these are like assigning the X values, okay? So really, technically, we can insert those x's in to our Ksp expression, right? So this is going to be x times x, which is really x squared. So anytime you have a 1-to-1 ratio, your molar solubility, which is x, this value of the formula unit, we're looking for that molar solubility of the formula unit, is always going to be x squared. That will be the ratio setup and how we do that for calculating molar solubility. Now, when it has a 1-to-2 ratio, as you see, it's 4x to the third. How do we get that 4x to the third? Well, let's take a look at here. So our generic, write out the generic. This is going to be something like AB2, a 1-to-2. Still gives you the A, but this is now a 2 plus, right? This is solid. And we're going to get 2 of our B minuses, right? So we have x of this, right? Every time it breaks apart, you're going to get one of these. So that's like 1x. But how many of those are you going to get? Every time that one breaks apart, you get double of that. So this would be like 2x now. Does that make sense? So if we wrote out our Ksp expression, we would get the concentration of the A here. And this would be the B concentration raised to the second power. So if you think about it, we would substitute in our x's here. So we would get Ksp equals x times 2x squared. And guess what that gives us? 4x squared times x, which ends up being 4x to the third. So that's how we derive that 4x to the third. Now you can go ahead and write out the expression, derive it each time, but if you just memorize these patterns, once again, that's the time issue. You go faster with the problems. If you're like, oh yeah, it's 1 to 2, it's 4x to the third, I can plug it in and do it quickly. Okay? So if you memorize those, you can still derive them. I mean, if you want to go to the expression, stick in the x's, do that whole thing, it's fine with me. But instead, trying to train you to become faster so that you don't waste time on the test. Okay? So that's how we get the 1 to 2. Now, some examples of like a 1 to 2. There are a couple different ways this could go. Okay? If we have, you know, PB, Cl2, that's just 1. But you could also have something like copper 1 carbonate, right? This would be copper 1 carbonate, where copper is a +1 charge. So you could have the 2 being the cation and the 1 being in the anion. You can have it that way too. So it doesn't really matter if the cation's 2 or the anion's 2. It just has to be a 1 to 2 ratio. But you'll still get that 4x to the third derivation. Now for the 1 to 3s. You're going to get 27x to the fourth. Let's see if we can derive this. So in this case, I'm going to do it this way. I'm going to do the A3B. Okay, so we'll make this this is going to be +1 here. 3 of them, and then plus the B is a 3 minus. So this time I'm making the cation be the singular one. So then Ksp would be A raised to the third, B3 minus, and once again our molar solubility here, x, right? So every time that one breaks apart, you're going to get 3 times the x of A, and you would get just x of the B. So you just get one of those every time it breaks apart. Comparison. So really, in here we would insert the 3x, and this would be x. So what's 3 times 3 times 3? So this is going to give you 27x to the third times your x. So what do we end up with? 27x to the fourth. So anytime you have a 1 to 3 ratio, you're going to end up getting 27x to the 4th as a quick way to plug and chug your Ksp. Now, ones that are like this, aluminum hydroxide, that 10 to the minus 33 one I showed you, that's one like that. So that's plus 1. Oh, silver phosphate would be another good example of a 1 to 3 one. 1 phosphate every 3 silvers. Okay, so these are examples that would fit this 1 to 3 ratio. And the fun one, the 2 to 3, 108x to the 5th. So that could be very similar to the aluminum carbonate example that we did. Al2, CO3, right? Or even the bismuth one, bismuth sulfide. That one would fit this type of ratio, okay? So A2, B3, got S on the brain, breaks apart, we get A, which is going to be a 3 plus, 2 of them, and 3 of the B minus 2s, B minus 2, AQ, Q, and so for every one of those, we're going to get 2 of these and 3 of those. So if we input that into our Ksp expression, which would be A to the 3rd raised to the 2nd power, B to the 2nd raised to the 3rd power, substituting this in, we end up with 2x squared times 3x to the 3rd. Right? So this ends up being 4x squared times 27x to the 3rd, which ends up resulting in 108x to the 5th. So anytime you have a 2 to 3, it's always 108x to the 5th. So you memorize those ratios, you can plug them in, get them done very quickly. Feel free to derive it each time, though, if you really want to. But it's still kind of following the same, pattern, too, from equilibrium Rice charts. You had your, what are you going to lose from this side? What are you going to gain on this side? So if this is, we have 1x over here, we're going to gain 2x of that, we gain 3x of that. Okay? Every time that crystal breaks apart, that formula unit breaks apart, this is kind of what we're going to see. Now let's take a look at some problems we're going to do here. Calculate the solubility of silver chloride in water to give us the Ksp. So we want to use the equations we just derived. And what should we do first before we do anything else? Write the formula so we know the ratio. Very good. So silver chloride, silver is Ag with a plus 1, chloride is a minus 1, so this is just going to be AgCl. So what is this ratio? This is the 1 to 1. So now we're going to use the Ksp equals what? X squared, right? So all we have to do now, plug this in and square root it, right? Square root both sides. And what do we get for our X value? What's our molar solubility of silver chloride? I'm sorry? 1.3 times 10 to the negative 5 moles per liter. So that definitely falls in our insoluble side of things because it's less than that 0.001 molar. That's the saturation point. That's how much you can dump in there before it's going to start precipitating out, falling to the bottom, and do the saturation thing. This is that saturation point. This is how much I could put in the water. This is how much salt I could put in 1 liter of water, and it would stay dissolved. Because this one's, yeah, it's 10 to the minus 5. It's definitely insoluble. So barely anything is going to go into the water, right? I mean, not a whole lot, right? Keep that in mind. That's what we're talking about here. That's how much how many moles I could put into that liter, and it would stay dissolved. If I dumped more than that, the crystals would start to fall to the bottom. Okay? So we're going to kind of get that's that saturation point, that equilibrium point where it start falling to the bottom.
So I'll just be
This is the molar solubility. So we just calculated the molar solubility.
Oh, molar solubility is the one that it's greater than.
No, this is the molar solubility. The Ksp value was just telling us generally it's 10 to the minus 10. It's very insoluble. But this number is telling me this is how many moles I could put in 1 liter and still it would stay dissolved. If I put more than that in there, you'd see crystals fall to the bottom. At that particular temperature, of course. All right, so you guys try this one. It's a little bit different. What's different about it? It's going to be a 1-to-3 ratio. We have our silver phosphate, right? So AG3PO4. Okay, so you might have to look at this one a little bit differently. So which one do we use here? Ksp equals 27x to the 4. So 1.8 times 10 to the minus 18 is going to be 27x to the 4th. Everybody knows how to plug that into the calculator to be able to do the 4th root of something, right? Just to make sure. I don't know, some people are not as math savvy, although that's a key. It's under the math key on the graphing calculators. Okay? So what do you get there for your molar solubility, your X value? Okay, so X equals 1.6 times 10 to the what? -5 moles per liter. So that's how many moles I could put in a liter and it would stay dissolved. Be right at that saturation point. And that's that equilibrium point of the silver phosphate. Yes? These are some of the main problems you'll see with the Ksp is when you have carbon ions together. Ions in a solution, equilibrium is already dissolved in the solution, and then you add in an ion that's in the salt, basically. So one is already at equilibrium, it's at the saturation point, and then you're adding in something that goes with the salt. Like for this example, we have the barium sulfate, but I'm going to be adding in barium nitrate. Barium nitrate, remember, is going to give us a Ba+2, and then the nitrate ion. Okay? Actually, this would be a 2, so that'd be a 2. The nitrate's not really going to affect anything, but the barium is a common ion. So if I added this in there, I'm going to affect this part. I'm like adding stuff to that part of the equation. So which way is it going to shift or proceed if we're following the Chatelier's principle? We add stuff into the products, it's going to proceed towards the reactant. So that means it's going to form some solids. Stuff's going to precipitate out. And that's the general concept of the common ion effect that you really want to take away here. If you add in a common ion, it makes it less soluble. Takes away, decreases the solubility. The solubility will decrease, okay, and you'll see some precipitation. You'll see some salt start to fall to the bottom. Okay, so the common ion is important in terms of it really decreases the solubility of the particular salt. But it's already insoluble to begin with, which is kind of funny. So it's already insoluble, and it's going to decrease the solubility. But you also can, you will use the Chatelier's principle with these kind of questions too, remembering You know, if you add something to one side, it's going to go the opposite direction. Okay? Keep that in mind. So try to think of this conceptually. So our salt will start to fall out of solution. That's another way to do that. That precipitation falls out of solution, and we end up making our salt less soluble. So let's look at problems here with that. How's that going to look in terms of a problem? So I have silver chloride already at its saturation point. It's in there, it's already saturated, ready to go. I dissolved my 1.3 times 10 to the minus 5 molar in there, right? Remember that? It was 1.3 times 10 to the minus 5 molar. That was our molar solubility for silver chloride, right? From the previous problem. Okay. So if I introduce 100 milliliters of 4.00 times 10 to the minus 3rd molar of the calcium chloride, how is that going to affect my solubility? First of all, I need to kind of look here too at my calcium chloride. What's the common ion? Chloride is my common ion. That's what's up here. That's the common part. And how much of the chloride is in that particular compound? Calcium chloride is going to be CaCl2. So this is like a doubled concentration of the chloride, right? Because when we say 100 milliliters with a 4.00 times 10 minus 3, that's referring to the formula unit. We have to double that to get our concentration of our calcium chloride. And you're going to set up something like a modified rice chart here. Modified rice chart. Okay, so we end up here with our overall saturation. The silver chloride solid. I'm going to go ahead and erase this and we can re-put that up here. Okay, and then we have our silver and we have our chloride. Okay, oops, I guess I should redraw that because the R should be here, I, the C, the E. Okay, now because this is a solid, is it going to play in equilibrium? No, so we get to do that now for that side. Goodbye for the solid side. We don't really need that. Initially, we already have the saturation point, so we aren't adding any silver or any chloride initially. So this, well, we are going to add in the chloride with the calcium chloride. We're going to be adding it to it. So initially, we're going to have 0 for our silver in addition, but we are going to be adding in extra chloride now. We have to figure out how much we're going to be adding in that's extra. Okay? So initially, our chloride would start here. So what is going to be the molarity of our calcium chloride? What do we need to do that 4.00 times 10 to the minus 3 to get our total concentration for the chloride? Multiplied by 2. So the 4.00 times 10 to the minus 3 times 2. So that's going to give us 8.00 So I'm initially adding this in. Because if I was at equilibrium, wouldn't have been adding either one. But I'm adding in chlorine now to that equilibrium position. So this is an initial amount I'm adding in. Okay? So our change here, is going to be the X value. Okay, so at equilibrium, we should have X amount of the silver. And we're going to have X plus the 8.00 times 10 to the minus 3. Because at equilibrium, they both should have been X, but we're adding in that extra chloride. So it's now changing that equilibrium position and value. So we do our Ksp, and this is where it's going to get confusing, so try to stick with the math. Let's write out Ksp. Ksp would be the silver times the chloride. So this is going to be 1.6 times 10 to the minus 10 equals x times x plus 8.00 times 10 to the minus 3. Now, let's go ahead just for fun. We don't really have to do this, but I'm going to show you why. Now your graphing calculator, plug this in as your y1, plug this in as your y2, get your intersection, get your x, get your intersection, and tell me what it is. So what does your intersection say? Right? Is that what you got? Okay. Now, 2 times 10 to the minus 8 is a very small number, right? Okay. So, let's think about this. 8, so this is 0, 0, right? 0, 0. Correct? That is my 8.00 times 10 to the minus 3, right? If I add in my x value to it right here, because I'm supposed to be adding it in, right? It's going to be 0.00000, that's 5, right? 2 more. Am I right? 1, 2, 3, 4, 5, 6, 7, 8, right? Okay. So that gets me here. If I add those two together, significant digit-wise, does that really affect my overall change here? No. So this is where we get to eliminate that x. We get to take this x out and just do the simple math. Because that's not going to affect this value at all. So really, all I have to do to solve this, instead of graphing it and doing all that extra stuff, is take my 1.6 times 10 to the minus 10 and divide it by the 8 times 10 to the minus 3. So it simplifies your calculation a lot because this x value is so small, it's not going to change the overall scheme of things. Because if you try to add these two together, this is going to get dropped off because of significant digits anyway. Go ahead and do it that way. Take your 1.6 times 10 to the minus 10, divide it by the 8 times 10 to the minus 3. So this x is now gone, so it's really just x times the 8.00 times 10 to the minus 3. See what answer you get for x. It's the same answer, right? If you divide it, you still get, right? So we get to eliminate the x here. You're going to be allowed to do that in some acid and base problems too. The reason why we know we can do that is because this value is so small that that change is going to be so small. You get to eliminate the x's in the Ksp problems. You have to be careful when eliminating in acids and bases and Ksp, only if your Ksp values are 10 to the minus 3 or 10 to the minus 4. That's when it starts to get where it might actually count for something. But anything, I would say anything, 10 to the minus 5 or above, you get to eliminate the x every single time. Okay, so look at your Ksp value, look at your negative sign there. Anything above that's 10 to the minus 5 or smaller, you get to eliminate the x right off the bat. If it's 10 to the minus 3, definitely I would do the graphing and check the x that way. If it's 10 to the minus 4, you're usually good with eliminating, and it shouldn't affect the overall value. Does everybody understand why we get to do this with this, because it's so small, right? Yes? Oh, well, let's talk about why that matters now. Look, 1.3 times 10 to the minus 5. This is a very good question. This was our original molar solubility. But by adding in the calcium chloride, look what happened. This is much greater than this. So my molar solubility now totally decreased. It went from being 10 to the minus 5 to now being 10 to the minus 8. So a whole lot less was able to be dissolved when I added in that calcium chloride, that common ion. So that's significant in looking at, originally we could dissolve 1.3 times 10 to the minus 5 in there, moles. But now by adding in the calcium chloride, we can only dissolve 2 times 10 to the minus 8 moles per liter. So that's that showing you numerically how the solubility totally decreases when you add in a common ion. And that's the conceptual part of the common ion effect. It decreases the solubility of the original salt. Okay? Now, let's look at the next one. Good question. Thank you. All right. Solubility of silver chloride in, sorry, next question. Here we go. Calcium nitrate. Anybody have any ideas on this one? Yes. There are no overlapping or common ions here. True. So does it affect our molar solubility? No. So guess what our molar solubility is still going to be? The 1.3 times 10 to the minus 5. It does not change unless there's a common ion affecting it. True. Very good. No common ion, your molar solubility at that equilibrium position stays the same. Very, very good. I'm glad that you saw that right away, because that was like a trick. That was one that they would throw in as a trick. You're looking for a common ion. There's no common ion. Doesn't change the molar solubility at all. Very good. Okay. Now let's talk about whether or not it's going to precipitate or keep dissolving. You do have some K versus Q problems here, reaction quotient as well. Except for what we're looking at here in terms of reaction quotient, the Q values is as its equilibrium system is already saturated. So the Q is going to tell you initially, you compare it to Ksp, and it's going to tell you if you're going to get a precipitate out of it or if you can keep dissolving stuff in the water. So I put it up here to be just like before, those alphabetical arrows, right? Okay, so basically if the Ksp or the Q is greater than the Ksp, the shift would be, or the proceed would be towards the solid. Solid over here on the, reactive side. And if the Ksp is greater than the Q, like this, alphabetical arrow pointing this way, you're going to be able to keep getting ions, the AQ out of it. So it's just like the equilibrium ones. If we put K first alphabetically, then Q second, you're going to be able to tell which way it's going to proceed. Is it going to form the solid, or are you going to be allowed to keep dissolving and form AQ, some more ions? Does that make sense? So I did it just like we did for the equilibrium ones, in comparing K and Q. Okay, and it will keep dissolving until you eventually get, where Ksp and Q are equal. You get that equilibrium position equal. So the confusing part, though, is initially you're starting with two separate solutions that are going to be dumped together. Sort of solution stoic from Unit 1. Okay? So let's take a look at our problem here. The Ksp for silver phosphate, I'm going to write out that silver phosphate first. Okay? Our silver phosphate is 1.8 times 10 to the minus 18. Oh, that's pretty small. Now, what you have to think about here is we have like two separate beakers, okay? In one beaker, we've got silver nitrate floating around, right? Over here in the other beaker, we've got sodium phosphate floating around. Right? Okay. We have two separate beakers that have two separate concentrations and amounts. In this one, it has 20 milliliters of 0.020 molar. And this one, we've got 80 milliliters of 0.0030 M, right? So they're separate. Now we're going to put them together, and what's going to happen when we put them together? We're looking for the reaction or the equation of the dissolving for the silver phosphate. So that's really what we're looking for. We're looking for the silver phosphate overall. We're looking for this. Is it going to be at equilibrium? Are we going to see crystals fall to the bottom when we combine them? Or is it going to allow us to keep dissolving more? Okay, so really, that's what we're doing. We're dumping the two together. So everybody have a visual kind of idea of what we're doing here before we proceed? Now, you have to think about this in terms of my initial concentrations. Okay? So, and really, which two ions do we need to focus on here? We need to focus on this one. So the nitrate's just a spectator. And we need to focus on our phosphate, and the sodiums are spectators. They don't matter, right? And if you look at in their formulas, silver is 1 to 1 here, so we don't have to worry about doubling or tripling or anything to our concentration. And in this one, the sodiums are tripled, but the phosphate's still 1, so we don't really have to worry about doubling or tripling that concentration either. Okay? Although if you had one where you had to, you're starting out with that, you would double or triple the concentration for them if they had a subscript. You see what I'm saying? Okay? So let's think about how are we going to figure out their concentrations once we put them together. When you dump two things together, what happens to the volume? The volume is going to increase. So we have to calculate it based off of the new volume to figure out the concentration. What's the equation we use when we're calculating the new concentration when we put new volumes together? M1V1 equals M2V2. Yes, we're going to use that one. Okay? And we have to do it for both. So, what's our new volume going to be? The 20 plus the 80, right, gives us 100 milliliters. So there's our new volume. Got to know that. Now for our silver nitrate. Let's do that one first. We start out with 0.020 molar times the 20 milliliters equals our M2 times the new volume, which is 100. So what is going to be our M2 of the silver nitrate? What's the new concentration for silver nitrate? 0.00. Okay, so this is for our silver. The concentration for our silver. Now we also have to do the same for our phosphate. Okay, so our sodium phosphate. We should chart on that. Okay. So we have 0.0030 times the 80 M2. And what is our molarity for that? 0.24 M, and this is for the concentration, basically, of our phosphate. Right? So now we know our initials, and what do you do with the initial values when you had Q for regular equilibrium? You plug them into the what? The K expression. In this case, it's going to be a Ksp expression. So let's look at our Ksp expression here. Did we write out our expression? No, we didn't write it out. So the Ksp expression is going to be what? Ag plus raised to the third power because of the 3 times the, okay? Now we know our initial concentration. So really we're solving for Q here, not Ksp, we're solving for Q. We're just using it to solve for Q. So we would plug in our 0.0040 raised to the third, plug in the 0.0024, and what do we get for that Q value? What's the number we get there? 1.5 times 10 to the minus 10, right? What you got? That's correct. Now, this is what we need to worry about and care about. What was Ksp again at the top? Okay, so this is definitely smaller than our Q value, right? That's Q, right? So, which way is it gonna precipitate, or can we dissolve more? Going this way, towards the solid, so we're gonna be able to, or it's going to precipitate. So you're gonna see Ag3PO4 crystals fall to the bottom of the beaker. Does that make sense? So we know that we're going to see some crystals fall to the bottom. Okay? And there you have it. Precipitation occurs. You have crystals at the bottom.